Imagine stepping onto a train that never actually touches the ground. No wheels rolling on steel rails, no grinding noise, no vibration from metal against metal. Instead, the entire train lifts itself into the air, floating just a few centimeters above the track using nothing but powerful magnetic fields. Now imagine accelerating from 0 to over 430 kilometers per hour in just 4 minutes. A journey of only 30 kilometers is over before you've even finished checking your phone. It sounds like science fiction, but every day in Shanghai, thousands of passengers experience exactly that. This is the Shanghai Maglev, the fastest commercial train on Earth. But this isn't just a story about speed. It's the story of a German engineering dream that found a home in China. It's the story of billions of dollars, revolutionary technology, impossible ambitions, and one tragic accident that reminded the world that even the most advanced machines can never completely eliminate human error. If you enjoy engineering, megaprojects, and the incredible stories behind modern technology, make sure to subscribe. Now let's discover how humanity built a train that can literally fly, a dream born in Germany. Our story doesn't begin in China. It begins more than 50 years ago, in Germany. Back in 1969, German engineers began working on an idea so radical that many people believed it would never leave the laboratory. The project was called Transrapid. The idea was surprisingly simple. Traditional trains lose enormous amounts of energy because their steel wheels constantly rub against steel rails. That contact creates friction, and friction limits speed. So engineers asked a bold question. What if the train never touched the track at all? If magnets could lift the train into the air, friction would almost disappear. Without rolling resistance, trains could travel hundreds of kilometers per hour faster than conventional rail. It sounded impossible, but physics said it could work. For years, German scientists experimented with different magnetic systems. Prototype after prototype was built, each one becoming faster, quieter, and more stable. Finally, in 1980, Germany constructed a dedicated 32-kilometer test track in Lathen. For decades, engineers tested hundreds of thousands of kilometers on this line. The technology became incredibly sophisticated. By the late 1990s, the newest model, the Transrapid 8, was approved for fully automatic operation. Its design speed exceeded 500 kilometers per hour. Germany had created one of the most advanced transportation systems on Earth. But there was one problem. Nobody wanted to pay for it. Cities loved the technology. They just didn't want the enormous construction costs. Years passed. The world's fastest train had nowhere to run then. China made a phone call. China takes the biggest risk at the beginning of the 21st century. China was transforming at an unbelievable pace. New airports, new highways, new skyscrapers, and an entirely new transportation network. Instead of simply copying Japan's famous Shinkansen or Europe's high-speed rail systems, China wanted something that would shock the world, something nobody else had successfully built. In January 2001, China signed an agreement with German companies to construct the world's first commercial high-speed maglev railway. Construction began on March 1st. Engineers worked around the clock. Thousands of workers transformed the project from blueprints into reality. Only 2.5 years later, the impossible had become real. A 30.5-kilometer magnetic railway connected Longyang Road Station with Shanghai Pudong International Airport. The total cost reached approximately 10 billion yuan, or around 1.3 billion US dollars at the time. Then on January 1, 2004, history was made. Passengers boarded the world's first commercial high-speed maglev train. This wasn't a technology demonstration. This wasn't an experiment. This was everyday public transportation. How does a train float? This is where the engineering becomes truly fascinating. Unlike ordinary trains, the Shanghai Maglev doesn't ride on top of rails. Instead, it wraps around a specially designed guideway. When the train reaches roughly 150 kilometers per hour, powerful electromagnets lift it approximately 10 millimeters above the track. That tiny gap changes everything. Because there is no physical contact, there's almost no friction. Instead of wheels pushing against rails, electromagnetic forces pull and push the train forward continuously. Think of it like surfing on an invisible magnetic wave. Since there's almost no mechanical resistance, the only major force slowing the train down is air. That's why the faster it goes, the more electricity it needs. In fact, engineers estimate that nearly 64% of the train's energy consumption goes into overcoming air resistance while traveling at top speed. Speed isn't cheap. The numbers that amazed the world. The Shanghai Maglev quickly became famous for one reason: its speed. Its normal operating speed reached 431 kilometers per hour. To put that into perspective, that's faster than many small airplanes during takeoff. During a special test run in November 2003, the train reached 501 kilometers per hour. Its theoretical design speed is even higher, around 505 kilometers per hour. Because the route is relatively short, passengers only experience maximum speed for about 50 seconds before the train begins slowing down for the airport. Still, the entire journey takes only about 7.5 minutes. Driving the same distance through Shanghai traffic could easily take 45 minutes or more. For nearly 2 decades, from 2004 until 2021, the Shanghai Maglev held the title of the world's fastest regular commercial train. It even earned a Guinness World Record. For many visitors, the ride itself became a tourist attraction, not because of luxury, not because of comfort, but because very few people on Earth have experienced traveling at more than 430 kilometers per hour on the ground. Can a Maglev train crash? At first glance, the answer seems obvious. Probably not. After all, Maglev trains can't derail in the traditional sense. They don't sit on rails, they wrap around the guideway itself. Even if strong winds hit the train, it remains locked around the track. The control system also keeps trains separated automatically. If 2 trains occupy the same section, the system adjusts their speed to maintain safe distances. On paper, it appears almost foolproof. But then came September 2006 on Germany's Lathun test track. A Transrapid train accelerated to nearly 450 kilometers per hour. 34 people were on board, unknown to the operators. A maintenance vehicle had accidentally been left on the guideway. The automatic emergency braking system activated exactly as designed. The train slowed dramatically, but physics has limits. At the moment of impact, the train was still traveling around 162 kilometers per hour. The collision killed 22 people and injured 11 others. It became one of the worst accidents in the history of magnetic levitation technology. Investigators later concluded that the technology itself had not failed. The braking system worked, the magnets worked, the train worked. Human procedures failed. One forgotten maintenance vehicle defeated one of the safest transportation systems ever built. The accident changed safety regulations forever. Inspection procedures became stricter. Communication systems improved. Maintenance protocols were redesigned worldwide. Sometimes, the weakest part of any advanced machine isn't the machine itself. It's the people operating it. Why didn't Maglev conquer the world? Considering its incredible performance, you might expect every country to build Maglev railways, but that never happened. Originally, China considered extending the technology all the way from Shanghai to Beijing, a journey of roughly 1,300 kilometers. The estimated cost reached nearly £15.5 billion. Then reality arrived. Building maglev lines costs significantly more than conventional high-speed rail. Every kilometer requires completely new infrastructure. Existing railway tracks can't be reused. Stations must be specially designed. Maintenance equipment is unique. Even the electrical systems are different during its early years. The Shanghai Maglev reportedly lost more than 1 billion RMB because passenger numbers weren't high enough. Meanwhile, China's conventional high-speed rail network expanded rapidly. It was slower than Maglev, but much cheaper. It could connect directly with existing railway lines. It was easier to build, easier to maintain, and easier to expand across thousands of kilometers. In the end, China made a practical decision. Instead of chasing maximum speed, it chose maximum coverage. Today, China operates the largest high-speed railway network on Earth. Most of it uses conventional steel wheel trains, not maglev, a legacy that changed transportation even though Germany never built a national maglev network. Its research changed the future. Engineers around the world studied Transrapid's achievements. Japan developed its own magnetic levitation technology known as SC Maglev, using a different suspension system. Japan pushed speeds even higher during testing. Commercial operation is expected to transform travel between Tokyo and Nagoya in the coming years. The philosophies, however, remain different. Japan focuses on redundancy, reliability, and an extraordinary safety record. China demonstrated bold ambition, proving that futuristic transportation could become a commercial reality. Neither approach is completely right. Neither is completely wrong. One prioritized caution. The other prioritized innovation. Together, they pushed railway engineering further than anyone thought possible. Conclusion: so the next time you land at Shanghai Pudong Airport and step aboard that silent train, remember, you're not just riding the fastest commercial train on Earth. You're riding half a century of engineering research, a German dream, Chinese ambition, billions of dollars of innovation, and decades of lessons learned through both success and tragedy, because the Shanghai Maglev proved something extraordinary. Floating trains aren't science fiction anymore. They're real. But even the most advanced technology can never replace discipline, responsibility, and human judgment. And perhaps that's the fastest lesson humanity has ever learned. If you enjoyed this story, don't forget to like the video, subscribe to the channel, and join us for the next engineering journey. Until next time.